everyone and welcome back to SK1 and we're back again with another video of mine and आज हम लोग about the uncertainty principle discuss करेंगे and this is basically going to be a proof for the generalized uncertainty principle. Now यहाँ पे generalized uncertainty principle and we'll use this principle to show how Heisenberg's uncertainty principle, the original one, the original uncertainty principle is actually quite true according to mathematics as well. So let's just get to the point. यहाँ पे जो generalized uncertainty principle है, so we speak of any two observables. Let's have them for instance A and B, and ये कुछ भी हो सकते हैं. They can be position and momentum. They could be position and energy or momentum and energy and any two such kinds of observables. And उनके लिए एक uncertainty principle we can find if there exists one. And how do we know that there exists one uncertainty principle for any two operators or for any two observables? Well, we can see that shortly. पहले I want you to think of any two observables A and B. तब यहाँ पे अगर मैंने A and B select किया है, one very important thing that you have to notice. One very important thing कि since हम लोग uncertainty principles की बात करें, here A and B should have some operators. So here we have A caret and B caret, some Hermitian operators to speak. अगर हम लोग time की बात करते हैं, so you often find yourself studying energy time uncertainty principle. तो क्या यहाँ पे time एक observable है? And is this uncertainty in time that we speak of actually the standard deviation in the values of time upon several measurements? Well, actually it's not. Energy time uncertainty principle काफी misleading हो सकता है in its concept if you really don't know how it is derived or its proper concept. So that will be the topic of discussion for some other video. One thing that you have to understand, that time has no operator in quantum mechanics. तो यहाँ पे हम लोग ऐसे कोई भी दो observables select करते हैं, their operators A caret and B caret and their Hermitian operators. उसके बाद what I can say is कि जो मेरी standard deviation होगी in the value of A, उसका square. So what you are doing is you are picking out a wave function and मैंने एक measurement किया and that measurement for the value of A, and I have not performed a single but several measurements and I have the standard deviation in the value of A and I square that. What should it be equal to mathematically according to mathematical predictions? Well, it should equal the expectation value of A minus the expectation value of A. That should be equal to, in fact इसका square के equal होना चाहिए, right? Sorry, यहाँ square यहाँ पे. So this is basically one way how you actually calculate the standard deviations. So what it can tell you is, since हमें पता है expectation value of any quantity क्या होती है. If I speak of the expectation value of A, I know it should equal the inner product of the wave function, क्योंकि ये हमारा पूरा सिस्टम एक वेव फंक्शन से डिफाइन हो रहा है. एंड व्हाट यू डू इज दैट you basically when you make a measurement of the observable A on it, तो wave function collapse कर जाता है, so to speak, and when it collapses it will basically give you a result of this observation of this particular observable. So the inner product of the wave function with A caret, the corresponding operator of the observable psi wave function, that's it. तो वैसे ही मैं expectation value of this A minus expectation value of A square define कर सकता हूँ. And what should it equal? Well, it should obviously be equal to the expectation value of, here you have psi, sorry, that the inner product of psi with A caret minus, ये हमारा constant term रहेगा because it is already an expectation value. So it is not a function, it is not a vector, it is just a number, square psi. यहाँ पे एक चीज अब मैं कर सकता हूँ, what I can do is कि since it is A caret minus expectation value of A, so let's just call it mean A times A caret minus mean A psi. हम लोग इसे लिख सकते हैं, since they are Hermitian operators of course, the expectation value inner product of A caret minus mean A psi and a caret minus mean a psi. Now इस चीज को मैंने लिख दिया as the inner product of a function f with itself, where the function f is defined to be a caret minus mean a on psi. So this is how I defined it to be. Now similarly observable b के लिए हम लोग क्या कर सकते हैं? We can similarly write for observable b the standard deviation square should be the inner product of some function g with itself. And what is this g? Well, this g is now defined to be, it should be defined to be b caret minus mean b on psi. तो ऐसे हम लोगों ने सिग्मा ए स्क्वायर एंड सिग्मा बी स्क्वायर कैलकुलेट कर लिया है in terms of these functions f and b that we have defined to be these particular functions that we get by operating this one Hermitian operator on psi. अब यहाँ पे एक चीज अगर हम लोग देखें, सिग्मा ए स्क्वायर टाइम्स में सिग्मा बी स्क्वायर, this should clearly equal this the inner product of f with itself times the inner product of g with itself. And अगर आपको स्क्वाश इनइक्वालिटी के बारे में पता है which is basically linear algebra, this number is always greater than or equal to the inner product of f and g. This is always greater than or equal to inner product of f and g. अब अगर ये f and g के inner product से greater है या फिर उसके equal है, here you consider what is the inner product of f and g. Well, the inner product of f and g should be equal to the inner product of a caret minus expectation value of a psi and b caret minus expectation value of b psi. And here what we basically have is the expectation value of a caret. Now this is basically inner products, all right. So here you could have expectation value of a caret the यहाँ पे it gets a little confusing, so just let me write it out full. This can be written as inner product of a caret psi with b caret psi, right? उसके बाद में you can basically clearly write it as minus the expectation value of a times expectation plus में times expectation value of b inner product of psi with itself, which of course should equal 1 for any normalized wave function. Here you have minus the expectation value of a, and here you have the inner product of psi with b caret psi, and then you finally have minus the expectation value. So यहाँ पे हम लोगों ने इससे ही मल्टीप्लाई कर दिया. Here you have the expectation value of b with the inner product of a caret psi with psi, right? So this is basically the result that we are getting. अब यहाँ पे एक चीज अगर आप देखोगे, here you have the expectation, sorry, inner product, so it gets a lot confusing with the notation. The inner product of a caret psi and b caret psi. How do you basically write this thing? एक चीज अगर आप देखोगे, they're Hermitian operators. So this inner product of a caret psi and b caret psi can as well be written as the inner product of psi with a caret b caret psi, and that will clearly be only the expectation value of a caret b caret, right? तो इस चीज को मैंने expectation value of a caret b caret लिख दिया. And remember, it's not the expectation value of a and b, it's the expectation value of a caret b caret. Why? The reason I'll explain shortly. Plus में mean a mean b, the expectation value of b caret you might write, or clearly यहाँ पे एक single operator है, will merely write it as b only. So here we have mean a mean b minus, now this can again be displaced over here, mean b mean a, they are numbers. यहाँ पे मैंने this expectation value of a caret b caret क्यों लिखा है? Well, the thing is कि यहाँ पे एक single operator नहीं है. If there were a single operator, So you could basically write it the expectation value of the observable itself, but you cannot write here because there are two operators and next to each other that are operating on the wave function. So it is actually the expectation value of the operator itself. अब यहाँ से इसको मैंने इससे कैंसिल कर दिया. So here you have a caret, b caret की expectation value minus mean a, mean b. Similarly, अगर हम लोग चाहें, so what we can also find is the inner product of g and f, and that should just be the conjugate of the thing, or you should be able to find it just with this process. And the inner product of g and f should come out to be the expectation value of b caret a caret minus this thing again, which is of course these are just numbers, so you clearly know that they are just the same whether you write it as mean a mean b or mean b mean a. The thing is, why are you even bothering to find the inner product of f or g or g of f, which is just its conjugate? Well, the thing is कि यहाँ पे अगर हम लोग कंसिडर करते हैं, एक बहुत ही इंटरेस्टिंग चीज होती है कि ये जो इनर प्रोडक्ट है ये आपको एक कॉम्प्लेक्स नंबर देता है, एंड दिस गिव्स यू अ कॉम्प्लेक्स नंबर. एंड आपको पता है कि किसी भी कॉम्प्लेक्स नंबर के लिए you find its square should be equal to its real part square plus the imaginary part square, जो कि obviously greater than or equal to होगा to solely its imaginary part square. And why so? Well, it should be equal to greater than or equal to, first thing you are squaring the terms, so they are coming out to be positive. यहाँ पे आयोटा तो इंक्लूड कर नहीं रहे, ऐसा नहीं है कि व्हेन आई से इमेजिनरी पार्ट तो इसमें मैं आयोटा भी इंक्लूड करूंगा और दैट वुड फॉर्म द कंप्लीट कॉम्प्लेक्स नंबर इटसेल्फ. तो यू बेसिकली फाइंड हियर शुड बी ग्रेटर देन और इक्वल टू द इमेजिनरी पार्ट स्क्वायर. So and the imaginary part square can as well be written as 1 over 2 iota z minus z conjugate. So this thing is square, and we know that since this inner product of f and g is basically a complex number, इसका अगर आप स्क्वेयर करते हो, one thing that I forgot to write here, one basic little algebra mistake, यहाँ पे स्क्वेयर होगा. तो इसका जब आप स्क्वेयर करते हो, so this should basically be equal to, and when I say square करते हो, so obviously square of the modulus, this should be greater than or equal to 1 over 2 iota z minus z conjugate whole square over this entire thing. So the very same thing can be said for the inner product of f and g as well. So what does that mean? Well, that means that the inner product of f and g should basically be greater than or equal to 1 over 2 iota, and here you have z minus z conjugate, तो ये वाला टर्म इस टर्म से कैंसिल हो जाएगा. You will have the expectation value of a caret b caret minus the expectation value of b caret a caret, right? And इस पूरे टर्म का स्क्वायर, so you might as well write it as the expectation value of a caret b caret minus b caret a caret, which is of course the commutator of the two operators a caret and b caret. तो यहाँ पे obviously हम लोग operators के साथ डील करें, so the order becomes pretty important. This is the expectation value of the commutator of a caret and b caret whole squared, and we know that this term is greater than this term and this term is greater than this term, is this term, so this term should of course be greater using the normal rules of logic, this term. तब यहाँ पे हमें क्या पता चला कि अगर ये the inner product of f and g का स्क्वायर अगेन इस चीज से बड़ा है, then sigma a square sigma b square भी इससे बड़ा होना चाहिए. So you get that the product of the standard deviation squared of the two observables should be greater than or equal to the whole square of 1 over 2 iota the expectation values of the commutator of the two operators. यही होता है हमारा generalized uncertainty principle. This is the generalized uncertainty principle. इसी चीज को अगर आप देखते हो तो this encompasses all the kinds of uncertainty principles that you can think of. Now it's like आपने कोई भी दो ऑपरेटर्स यहाँ पे रखे and उनके और कम्यूटेटर का एक्सपेक्टेशन वैल्यू यहाँ पे कंसिडर किया, वेल देन यू गेट कि इनके स्क्वायर ऑफ द स्टैंडर्ड डेविएशन का प्रोडक्ट शुड बी ग्रेटर देन और इक्वल टू व्हाटएवर नंबर यू आर गेटिंग, एंड दिस इज रियली अ रियल नंबर, अ रियल पॉजिटिव नंबर जो कि यहाँ पे आपको हमेशा मिलता है. वेल हियर्स एन आयोटा. So the expectation value of the commutator is also going to contain an iota which basically cancels out with this one. Let's see how. If you consider the first observable to be position and the second to be momentum, हमें पता है according to the canonical commutation relation, the commutator of position and momentum operators is iota h bar. तब जब मैं यहाँ पे iota h bar रखता हूँ which is basically a constant number, तो इसकी expectation value वही होनी चाहिए. So we know that the expectation value of the commutator of x caret and p caret is just iota h bar. Iota को मैंने यहाँ पे रखा, so iota से iota cancel हो गया, and I'll find that sigma x square, sigma p square should be greater than or equal to h bar over 2 का whole square, and then we basically get that sigma x sigma p is greater than or equal to h bar over 2. And there you have Heisenberg's uncertainty principle. तो यहाँ से Heisenberg's uncertainty principle easily आप derive कर सकते हो, and जो भी दो quantities in physics या in quantum mechanics commute नहीं होती हैं, उनके operators commute नहीं होते, so these kind of quantities जो commute नहीं हो सकते उनके लिए हमेशा एक uncertainty principle exist करता है, which can be easily explained by this one. Like you can possibly think of the uncertainty principle for the position and the Hamiltonian, that is the energy operator, and you can easily come up with that uncertainty principle. You will in fact find it to be that the sigma x square sigma h square should be greater than or equal to 1 over 2 iota the expectation value of momentum whole square. That is the uncertainty principle for the position in the Hamiltonian operator. Well, what does this principle actually mean? I have already told in previous of my video, so there is no need for explanation on that one. This is the very abstract, you see, and the proof is really abstract. So this is the abstract proof of the generalized uncertainty principle. What we have mostly done is actually linear algebra. That was all for today's video of mine, and thanks to all of us.